Oké, akkor sziasztok, Nicola Wrachen vagyok, és azt mondta a kislányom, hogy nem tudok beszélni magyarul, és akkor sajnálom, angolul fogok beszélni. And so I'm going to talk about porting Doom. Is there anything? Okay. I'm going to talk about porting Doom and Quake to microcontrollers. So this is the agenda. First I will make a very brief introduction, then I will talk about Doom, then about Quake, and then I will conclude. And I feel obliged to tell you that it may be quite boring, so proceed at your own risk. So to introduce, are these retro games, that is Doom and Quake, and yes, I would like to, some people would say, oh, retro games are only 8 or 16 bits, but I argue that they are, because they are almost 30 years old, and also they did not make any use of accelerators, and they were the first of their kind. And also Retro Radio plays 2020 songs as well, so basically we are well within range. So what we are talking about? We are talking about porting Doom and Quake to systems with a microcontroller. What is a microcontroller? Is basically an integrated circuit with CPU and some supporting circuitry, some RAM, some ROM, maybe flash, and some peripherals, and also such as like serial or parallel GPIOs. And the specifications may vary, but in this case, in my work, I'm talking about the Cortex M4 or M33 between 64 and 80 megahertz, unless I overclock later. And they have between 1 and 1.5 megabyte of flash and 108 or 276 kilobyte RAM, including 20 kilobyte for the radio, because these are radio system on a chip. And the introduction, why Doom? So yes, I had an Amiga 500 Plus when Doom came out, and I was fascinated how could Doom create realistic perspective image so fast, where, for instance, the Lux Paint was so slow in the perspective mode. And I could play 3D games only in 1996 when I bought an Amiga 1200s, but they were not Doom. And Doom, it came out in 1998. So there is also Doom, as the previous speaker said, Doom running on everything, for instance, on a camera, or even in the Windows taskbar, or even Doom running in Doom. So, but there was a major trigger in 2020, especially in September 2020. There was Doom running on a pregnancy tester, but and the press caught this and say, oh wow, what an achievement. But the reality is that only the plastic case was kept in this port, and it was replaced everything, and basically Doom was being played on a PC, and let me open the laser if I can. Okay, I don't know. Can I? Just a second. I am quite back. Okay. Is it visible? Yes. Okay, so basically the scaled down video was basically streamed to the display through USB. But despite this was a fake news, actually, I was very inspired, so I wanted also to bring my contribution to the It Run Doom meme. So I ported this to several devices. So first a smart light bulb, and also a a BLE dongle, and also I created a small console to play Doom also with multiplayer. And the general block diagram of the target devices is the same, basically. There is the microcontroller, a serial display with different resolutions. Then there is external SPI flash for the data, for WOD, the Doom.WOD game, data game file. And also there is, of course, some inputs like keys or thumbsticks. And then, of course, the audio part, that is, it's generated either through PWM or DAC. Then there is a filter, an optional amplifier, and then you connect the speaker or headphones. And this is common both in Quake and in Doom. So, okay, how did I do this? Basically, I have a recipe. I choose a repository, and I want it to be very easy to start to develop with. And I want that it runs on Windows, basically. And I want it in C, so that I can develop in Windows and optimize for memory, and later I will port to the target device once I reduce the memory usage. Also, I don't want modern ports because they add additional features, and I don't want them because I need more effort to optimize them. I just want to have the original game. And as I said, I start with optimizing on Windows or on a larger embedded device, and then I will treat this like a game, not like an engineering task, because an engineer would say, I'm not doing this because it's very hard to shrink 4 megabytes in less than a quarter megabyte of RAM. And yes, first I have the game running, and then I will optimize for speed later. And ancillary stuff like settings and save games are done. I do this once I finished, basically, to have the port running on the target device. And why? Because this gives me motivation, basically. And let's start with Doom, basically. And you can see that there are a lot of source port in Doom, and however, I have chosen basically a derivative work of PR Boom, which is the port to the GBA, the Game Boy Advanced, and it was done by Doom Hack. And it's based on PR Boom port. And why? Essentially because it was already ported to an embedded system, that is the GBA, and basically there is just direct writes to a frame buffer, no drivers or whatever, and also there are no file handling stuff, so you just read from an array, basically. And also it was already optimized for a system which had just 348 kilobyte RAM, so I didn't have to reinvent the wheel. On the contrary side, the developer removed the ZDEP lighting. As you can see, here is the original. The farther walls are darker. Here instead it's removed. They are all at the same shade. And also, there were some GBA-specific optimization that really gave me headaches, and there was no demo compatibility, no multiplayer, and yes, so basically, how it's working, basically. The idea of this port is basically that the GBA had up to 32 megabyte memory mapped cartridge, and basically the majority of data in Doom, basically graphics and sound, they are constant, so they can stay in flash instead of being loading to RAM. But in our case, we have some issues. The first is that we don't have enough memory mapped flash like in the GBA, because the external flash I have added is a peripheral, is not a memory mapped. You can't simply dereference a pointer and read. you have to read from using, for instance, the MA into a RAM buffer first. And second, GBA had 340 kilobytes of RAM, and initially on the light bulb I had only 180 kilobytes of RAM. On later devices I had more. And first, I have ported Doom to a much bigger device. It had an STM32H7, which is a very powerful microcontroller, which had a lot of flash, a memory mapped QSPI, and 1 megabyte RAM. And it was a very small effort, very few days, including creating the hardware to port Doom onto this system. But later, I have optimized for RAM to go down to the 108 kilobyte goal, and I had added the functions so that I can read from the QSPI like if it was a peripheral, so that it was simple later to port on the target device. But I had to optimize 276 kilobyte out of 384 kilobyte. So we had to do some memory optimization. So first is, of course, reducing data size. How? Doom uses extensively pointers, and but we have only a quarter or less megabyte of RAM, so we have only 18 bits. But all the allocations are 4 bytes aligned, so basically we have only 16 bits. So a short is enough. And the conversion between a long and short pointer in using Cortex M33 or M4 is very easy. You just need 1 or 2 instructions. So also I have used, whenever possible, array indexes instead of pointers. Because if I have an array with like 1,000 elements, I just need 10 bits. And why 10 bits are okay? Because they don't fit, there is not a data type of 10 bits, but these are used in structure, so I can use bit fields. So, and also I can, for instance, I use some profiling to understand how big was actually the minimum size of each data in every structure. And also I have made, I had to reorder all the members to avoid paddings. Also, another optimization technique was splitting structures in constant and non-constant parts. That is, a constant part that is in a sector, the number of lines of the sector is constant, doesn't change. But the height of the floor or the ceiling will change, or even the light level. So the floor height and ceiling height and the light level will stay in RAM. Instead, the line count will stay in a structure, separate structure in Flash. Also, I have reverted to all Doom code because PR Boom used an enhanced allocator, which was based on malloc. Instead, in the original Doom, the zone memory was a replacement for the original malloc. So in the new code, basically I had 28 byte overhead. Instead, in the new one, I had only 8 byte overhead per block. And also, PR Boom instead added the pool memory allocation for a lot when you have a lot of objects of the same size. And I kept this feature, but I have optimized to just have 1 byte per block overhead. And then the most critical part was the object classification. So what is a MOBJ-T? It's a map object type, and it's basically a container that stores all the informations of every object in a map. And it can be a bonus, or a projectile, or a static element like a candlelight, or an enemy like the imp. And however, in Doom, there may be up to 500 objects at the same time. And in the GBA port, it was already optimized down to 140 bytes, which means that up to 70 kilobytes were, excluding overhead, were needed to store all the information. And this was too much for our port. And so using all the optimization I mentioned before, I was able to trim this firstly to 92 bytes, and then later on later port even down to 52 bytes. But still this is not enough, because it would take between 25 and 46 kilobytes of RAM, and by the way 46 over 108 kilobyte. So can we do better? And yes, of course, we can classify the objects, because half of the objects are static, like maps, bonuses. They don't move, basically. They don't have an enemy. And or they can be also partially static. That is, when you kill an enemy, it will drop off a bonus. Or when you kill in a multiplayer match, there will be the player corpse. But it won't move, so basically they will have a limited number of members. So we can use different structures sharing, however, a common part. So, and the game understands which one will use by checking the flag which are stored in the common part. So we have the static part, which also points to the XY position, which will be in flash for a fully static object like this candlelight or this bonus. Or these will be in a memory pool in RAM if they are quasi-static, like I said, the partially static object such as drop-off bonuses or corps. And there will be the additional full object parameters, which will have the entire structure. And basically, the static objects now occupy only 20 bytes, and partially static objects 29 bytes, and it was 44 in the first port. So basically, the occupation was between 18 and 34 kilobytes, and before it was basically double of this. And however, all these optimizations doesn't come for free, because you need a lot of instruction for extracting bit fields, and even if you modify a bit field, it's actually a read and modify write operation. So you add a lot of overhead, then you have the short to long pointer conversions, unaligned accesses, and many others. So I wanted to give better dignity to an 80 megahertz Cortex M33, and I wanted to improve performance. So the first speed improvement, and which is actually also a memory optimization improvement, is basically that take into account that we have at least 1 megabyte of flash, and the code size is very small, like 256 kilobyte, and with BLE it's like 400 kilobytes, but the flash is even bigger. So we have more than 750 kilobytes of flash, which would be wasted if not used. So also this flash is extremely fast, especially compared to the external flash, because we are talking about 100 megabytes per second versus 10 or 20 megabytes per second. And also the latency is at least 1 order of magnitude faster than external flash. So what we store here? Mostly randomly accessed data to have a better latency, and like the level data or floor and ceiling textures, and also some runtime generated read-only data, and all these basically would leave still like 300 kilobytes of unused flash. So I also fill the remaining space with as many wall textures as possible. Another improvement was getting rid of composite textures. What are composite textures? Basically, Doom has a uses patches, which are graphics element, as you can see here. There may be textures which are single patch texture, that is, a patch is actually the textures. But to improve variety, the designer created these multi-patch textures so that you superimpose many different patches. The problem is that if you want to draw this column, you have to basically load these textures, which is this, load this texture column, then load this texture column, load this texture column, and render to a separate buffer in RAM, and then use that buffer for the final rendering. And the solution that is used, for instance, in the GBA port is to use a cache to avoid all this overhead. But of course, we don't have enough RAM, so we should make all this operation every time, which is very costly in terms of speed. And the solution is that I have created a tool that basically expands, that pre-renders all the composite textures in a single patch texture, and they save in the WOD file. This means that the WOD file will increase in size, and I was afraid it would increase like by 10 megabytes, but actually it only increases by between 1 and 2 megabytes in the full Doom games file. So it's not an issue on our case. And another improvement was asynchronous column loading. As I said, as you may know, of course, the rendering in Doom is done of walls, is done by column. And some of the texture may not fit the internal flash, so they need to be fetched from the external flash and copied to RAM before we can render them. And the naive way would be that I load the first column and then I render, then I load the second column and then I render, and so on. And this means that the sum of the rendering is the sum of all the operation. But we have DMA, so we can basically load the first column, and then when we are loading the second column through DMA, we can start rendering the first column, and repeat the second, this stuff by loading the third column while we are rendering the second column, and so on. So basically, we are saving this amount of time. So what about the results? I have ported to this system, I can show you later, with as low as 108 kilobytes of RAM. I restored ZDEP lighting, and also in bigger devices, I restored the screen melt effect, the multiplayer, and the speed is between 30 and 35 frames per second, which is basically the frame rate cap in Doom. What about Quake? This was a much bigger challenge. And yes, Doom is too easy now. Everybody is porting Doom, as said before. And especially now that you have bigger parts. So despite, in my case, I had added also BLE-based multiplayer. But I saw a video some years ago about Quake running on GBA, although very limited. And so it was feasible. And this time I didn't choose any pre-optimized code base. I used basically SDA Quake, which is WinQuake with the SDL, Simple Direct Library support. And following the mid-90 fashion, I also overclocked the CPU from 80 to 136 megahertz, despite the datasheet doesn't say it's not possible. And about optimization, okay, most of them are the same as in Doom, but there are many more new, and due to lack of time, I will only speak about a few of them. So, first of all, Quake C and edits. So, Quake C was a powerful scripting engine, language that defines behaviors of everything: monster, bullets, triggers, weapons, doors, and whatever. And it goes like this. You have the Quake C files, which are text-based in Quake C language. You give them to the Quake C compiler, and it spits out the progs data, which is a bytecode. And this bytecode is embedded into the game data file, the pack 0 pack, which is the equivalent of Doom WOD file. And this progs data is loaded into RAM, and it is 420 kilobytes. And there is also the progs data is loaded, therefore, and an array of edits is allocated, and progs data is executed by a virtual machine. And by the way, Quake had a server and a client on the same executable. And so basically, what are, by the way, the entity dictionary or edits? They are the equivalent of the mobj, okay, the map object, but much more complicated. And I said that an array is allocated, so all the edits has the same file. And the data types are floats, basically. And even if you have to count the number of ammo, it's a float. There is no int. And then there are vectors or string entity or script function, but they are all 32 bits. And of course, vector are 12 bytes. Sorry. And there were about 200 members. So if you have 800 bytes per object. So if you have 400 objects, you need 320 kilobytes of RAM just for storing the object information. And so I have modified the Quake C compiler to output actually C code instead of bytecode. And this C code generated C code is included in the project source. I got rid of the virtual machine because now everything runs natively instead from Flash. Okay, I don't need any RAM for this execution, and also it's also faster. And now I modified the code so that object members are accessed not directly but using getters and setters. And also objects are dynamically allocated in the zone memory. And in this way, I can optimize each object type. I can decide which object has which members, and also the member size and the data type. And basically, it's like the mobj, but taken to the power of 10. And yes, of course, it fit the memory. And what about another nightmare? It was the surfaces. So what are surfaces in Quake? So the world model is a complex 3D structure which is made by thousands of polygons, and each polygon is called a face. And to each face, a surface is associated. And what is a surface? A surface is a texture that you tile horizontally and vertically, like this. And then you have a light map grid, which has is every 16 pixels, okay? And you apply this light map to the texture, and then you obtain the lighted texture. However, real-time lighting of each frame is very slow, so Carmack got an idea, have a cache, because the same surface, like this or like this, is very likely to appear on next frames, because you turn very slowly, you have smooth movements. So, and also dynamic lights, which would require the recalculation of the lighted surface, are very, they are very limited in radius and very few per frame. So the idea is to put all these pre-lighted textures in a surface cache, and also this will really improve bilinear interpolation needed to have the smooth lighting. And the issue in our case is that Quake allocated 600 kilobytes for the 300 by 200 pixel resolution. And you can reduce the cache size, okay, but the minimum size is that a single surface must fit in that cache. And the issue is that there may be very large surfaces, and I saw that the maximum was about 70 kilobyte. It was a rare event, but it was there. And but this is very slow because it's not a cache anymore, because every time you are overwriting what you have put in the cache, because just basically one or few texture will be there. And for each texture, you have to load the texture. For each surface, you have to load the texture from the external flash, extend it to the surface by tiling, and then calculate the lighting. And this even as if a single pixel is going to appear in the frame. So I profiled that between 220 and 30 kilobytes worth of data need to be loaded from the external flash just for the surface rendering, which means at least 17 milliseconds just for load operation, by the way, on the overclocked device. So we need a completely different algorithm. And the idea is that instead of pre-rendering the surface texture in a cache, we are doing bilinear filtering and lighting on the fly. And the cons, of course, that bilinear interpolation is very, very expensive. Initially, it was like 100 cycles per pixel, and I was able to optimize in assembly to 30 cycles per pixel. On the pro side, basically, you don't have to do the texture tiling, and also textures are smaller than surface, because you need to tile texture to get a surface. So you are using much less memory, and given the same surface size. And you don't have to pre-render the entire surface if a few pixels are going to be drawn. And the same texture may be reused in many times, and this is spoiling next slide. But okay, with this and without doing anything else, I got an appreciable but not consistent improvement. But this opened the door to the next improvement. I will talk in a few seconds. That is now. That is, I realized by chance that the same texture is used over and over and over, because this is with lighting on, and you see, oh wow, it's a cool image. Okay, it's not really, you can't really see, okay? But if you turn off the light, you can see that it's almost the same texture used over and over and over. So basically, it's the surface lighting which is making the difference. And we can reuse the same texture instead of loading again and again the texture from flash to RAM. And how to improve this? By sorting the surface by textures. And there are only about 600 surface per frame maximum. So sorting is reasonably fast. And we must support a buffer, a texture buffer, which can hold at least a big texture. and which was about 30 kilobytes, more or less. But the majority of textures are small, so in many cases we would have a huge buffer and we are using just 1 or 4 or 2 or 4 kilobytes. So we can use the same buffer, and when possible we can load more than one texture. And we can also use DMA so that we can use the same trick we made before. That is, when we are rendering an element, we can load the next element at the same time. And this is an example. Let's suppose that we need to render 4 surface and they are using these textures. As you can see, these textures are used twice. So we are sorting for a texture, and then while this surface is being rendered, we are loading the next texture. And while this surface is being rendered, of course, next texture would be the same, but the algorithm will skip this and will check the next different texture and will start loading again. And of course, since there are only 4 surfaces, will do nothing during this and this. Another trick was memory reusage. So there are many buffers that have limited scope, and they can be used, however, for other scope-limited purposes. And basically, for instance, we have the texture cache buffer, which is this one, and the Z buffer, which is this one. But when we don't need the Z buffer or the texture cache buffer, we can use for many other purposes. So basically, 120 kilobytes are used for an equivalent RAM size of 375. So taking into account that we have 276 kilobytes of RAM, it's like if we had basically double the amount of RAM. And what about the performance? Oh, I forgot to say that for Quake I made a different console, but basically the microcontroller is the same as in Doom. And okay, it's very hard to see, but I have copied here the reference, and with overclock I got 29.2 frames per second, without its 17.1 frames per second, which means we are better than a Pentium 100 or a Pentium 60, respectively. And to conclude, so mid-90 games can be ported to memory-constrained systems. And yes, I have ported also Duke Nukem 3D. And the main idea is to keep constant data to flash. And by 1996 standard, even external flash is decently fast, especially for sequential operation, and also especially compared to hard drive, but also compared to RAM. Still, I needed a lot of RAM optimization. And Quake was the most difficult port I made, not only because of source optimization, but I had to create 4 tools. The optimizer of the pack files, which actually doesn't reduce the details, it just improves data loading. And the Quake C to C converter, the table generator, and the setter and getter generator for different object classes. And I want to tell that, yes, the game were not inherently poorly optimized for memory. The goal was to improve the speed because memory was cheaper than CPU speed. And then it's everything, so thank you for your attention.